Hello everybody. I hope that you're having a good weekend and hopefully this won't take too long, but I want to go ahead and get us started for Monday since we had so much fun at Pi Day today. But we are going to be talking, I think I want a different color. I think I'm going to go for pink. We are going to be talking about graphing reciprocal functions. And actually, I should say you might want to pause it right now and get graph paper. We are going to be graphing things today. And so I know there are some of you who are going to want to put your notes on graph paper. Now, when we are graphing reciprocal functions, the first thing that we are going to do is talk about our parent function. Now our parent function is just like our y equals x squared. It's just your basic function that we then move left, right, up, down, stretch, shrink, and reflect. So our parent function is actually going to be 1 over x. This is the first time we have really had a variable in the denominator when we have been graphing. I can't think of any other time. In fact, back when we started polynomial functions, we even said, we made it explicitly clear that our polynomial functions could not have a variable in a denominator, or that variable could not have a negative exponent. So now we're moving into what happens when we get a variable in the denominator. This graph actually has a special name. It is called a hyperbola. The hyperbola is going to be probably a graph that's a little bit different than what most of you have seen. I'm going to make a table, and I am actually going to plug in some values for x and y. We typically, when we're graphing, we're going to plug in things like -3, -2, -1, 0, 1, 2, and 3. So if we plug in a -3, then we're going to get 1 over -3, which isn't too much of a big deal. It's just going to be -1/3. So we go to -3 and go to -1/3. Pardon me. I went in the wrong direction. -1, 2, 3, and -1/3. We plug in a -2, that's going to be 1 over -2, or -1/2. The negative being the denominator or the numerator is the same. So we're right here. If we plug in a -1, we are actually going to get 1 over -1, which is just -1. So -1, -1 is going to give me a coordinate. We plug in 0, we get 1 over 0. And that doesn't work. The reason that doesn't work is because we could never, ever divide by 0. And so we've talked about this whole dividing by 0, and one other time we actually did talk about what happened that if you have in a graph where you are dividing by 0, we have an asymptote. Now, what this asymptote means is that we are not going to be able to have a point at all on where x equals 0. And so my x equaling 0 is actually my y-axis. And so there's going to be this line right here that we can get close to, really, really close to, but we can never touch. So that's not going to work. Now, if we go to 1, let's just see what happens when we plug in a 1. We get 1 over 1, which is 1. So now we're here. If we plug in a 2, then we're going to get 1 over 2, which is going to give us 2 and 1/2. Well, that's not a very good point. And then if we plug in 3, we're going to get 1 over 3. So what happens, and we see that this is starting to slope down kind of like exponential decay, because if you plug in a 4, we're going to get 1/4, and you plug in a 5, we're going to get 1/5. So it's going to keep getting closer and closer and closer and closer. But it is not, no matter what number you plug in for x, we are never going to actually get a 0. It's impossible for us to get a 0. So what happens is we have another asymptote with our reciprocal functions on the x-axis. So we actually, I should have made these a different color. We have an asymptote on our y-axis, and we have an asymptote on our x-axis. So the coordinates of our functions, if we were to plug in a 1/2, 1 divided by 1/2, if you keep it, change it, flip it, becomes 1 times 2/1, or 2. So at 1/2, we're going to be at 2. At 1/3, we're going to be at 3. So we're going to get closer and closer and closer and closer and closer to this asymptote, both in quadrant 3 and in quadrant 1. So this is going to be our reciprocal function. It is different than what we have seen before. Like I said before, it is called a hyperbola. And if we look at our domain is going to be all non-zero real numbers. Now what that means is we've got all reals except for x cannot equal 0. Our range is going to be the same thing. We've got all reals except y cannot equal 0. We cannot have a 0 for y because we have an asymptote at x equals 0 and at y equals 0. And if you remember, horizontal lines are y equals 0. That's my horizontal asymptote. And vertical lines, x is made up of v's, so x equals 0 is my vertical asymptote. If we're talking about intercepts, we don't have an x-intercept or a y-intercept in our parent function. They do not cross the x-axis or the y-axis, so you may want to make a little star, no x or y-intercept. I know, can't spell, can't read what I'm writing. It's Friday afternoon. And they also have here, I'm looking in our book to make sure that we write everything. They have it as not defined where x equals 0 and y equals 0. Once again, that is our asymptote. We know that we have an asymptote at x equals 0 and y equals 0. So this one is a little bit different looking. I know we haven't seen something like this before. You can say that x cannot equal 0. That is not a possibility for x to equal 0. But all of our reciprocal functions, anytime you see something with a variable in the denominator, you are going to have to recognize that there are going to be asymptotes involved because we cannot have a 0 in the denominator. Now there are lots of different reciprocal functions that we're going to look at. If we want to look at f of x equals 3 over x squared minus 6x plus 5, we can ask ourselves, where is this function not defined? Where can we not have a value for x? So in this particular format, it's not really helping us. In our original function, we just had an x in the denominator. So we knew that if we plugged a 0 in, that was not going to work. But once again, all of us should be screaming something when you see x squared minus 6x plus 5. All of us should be realizing this is a puzzle. If you were to do something plus something equals negative 6 and something times something equals 5, then we've got negative 1 and negative 5 as our answers. So this is going to factor into x minus 1 and x minus 5. Now, we can't say that our function is not defined at negative 1, because if we were to plug in a negative 1, that's not going to give us a 0. However, if you take your denominators, whatever your factors are in your denominator, and you set them equal to 0, that is going to show you the values that x cannot be. Because if you add 1 to both sides, that is going to give me x equal to 1 and x equal to 5. For this particular function, we can say that x cannot equal 1 and x cannot equal 5. Now, why does that matter? If I was to evaluate this function, 3 over x squared minus 6x plus 5, and I wanted you to find what happens if x equals 1. So we want to do f of 1. I'm going to have 3 over 1 squared minus 6 times 1 plus 5. Well, 1 squared gives me 1 minus 6 plus 5. And we should see 1 minus 6 is negative 5 plus 5 is equal to 0. So can 3 over 0 ever be a coordinate? No, doesn't work. So that shows us that we cannot have x equal to 1. And if we take x equal to 5 and plug back into our original function of f of x equals 3 over x squared minus 6x plus 5, if we have f of 5, then we get 3 over 5 squared minus 6 times 5 plus 5. So 25 minus 30 plus 5, once again, it's going to give us negative 5 and 5 or 0. So we cannot have 3 over 0. This isn't going to work. Well, it's Friday afternoon. I'm tired. You're tired. Hopefully this will give us a good start for Monday. I hope you all have a good weekend.